Okay, hello everybody. Congratulations on the national championship, Dominic. There. Boo, everybody. Nobody was actually a Notre Dame fan, right? I mean, come on. All right. Well, hey, how's everybody doing? How's your weekend? Doing good. Today's Tuesday, which is crazy. And it's going to be one of those weeks that it's like a hurricane over again, right? Except we're not like that afraid. It's more like excitement of hurricane. I'm sure everybody got a text already, right? You guys know. So half these slides are going to be obsolete because I wanted to talk about the lab and everything, but yeah. No, I'll talk about what means for lab tomorrow. Obviously, we're not going to have lab sections tomorrow. I'm still going to try to have them on Thursday, just because it's an easy first week back.
So you said for the people that have it tomorrow that we don't have it, but you want to come on Thursday?
Yeah, I will talk about that. Yeah, that's the plan.
Where's all about the homework, bro?
That's the way to say it.
I'm glad you agreed with that.
All right.
I mean, you always look at what you thank you.
Sweet, thank you. Okay, so for this week, I had written all this. It was literally back and forth and everything, and then we all got the text like 5 minutes before class started. So there is no labs tomorrow since we're all going to be in a blizzard. But what I do want you guys to do, goodness gracious, where is this echo coming from? Oh, well. What I would like you guys still to do is review the lab content on Canvas. So it's all posted on there, that little link on your Canvas page that used to like click and not work. Now it should work. There is a lab syllabus on there, and I'm going to go over those at the end of this class. That goes over the template of the lab report, and then kind of what to expect in the lab section of each time. So we're still going to have some energy put towards lab this week, even if we don't have a Wednesday lab. As of right now, the Thursday lab is still going to be on, weather pending. But with the Thursday being in the morning, we're still going to keep that scheduled, just so we're not too far behind. The other thing I was going to say was the Wednesday group. If you guys are able to and want to, please show or pick one of the Tuesday or Thursday lab sections to go to. They are at 10:50. Basically, it's like 10:50 till like 12:05. Yeah, 10:50, 12:05. If you can't make one of those times, then let me know. We can figure something out. It's a relatively like easy and fun lab. We're actually going outside and using hand augers and doing soil like stratification, and actually like working with soil and doing a moisture content. So if you can't make it, we can still figure something out, and we'll share the data. We'll add all the data together. So maybe that's it. I have no idea what's going on. So yeah, we'll figure that out. But anyways, no lab tomorrow. This is also canceled, so forget all this. Just go play in the snow. Be safe. Don't drive if you're from Florida. I do want to share this too. This is a cool opportunity coming up. It's with construction management. If you want to get plugged in the construction kind of sphere, has anyone heard of NESPA? Yeah, it's one of the world's many fun engineering acronyms. Northeast Florida Building Association. They every year do this cornhole tournament, and student teams are free. It's really fun. I went out last time. It's at their South Point Parkway facility, so the like headquarters or whatever, the clubhouse kind of thing. It's all in the parking lot. A bunch of engineering firms are there too. So, but if you want to get involved with like construction/civil, then I will share this on Canvas, and you can scan it. You can make student teams for free. They have a bunch of like barbecue and free beer and free whatever you kids drink nowadays. So yeah, it's a cool one, cool event out there. Give me just one moment, because I don't know where the sound is coming from. Is it coming from here? Just gonna turn that off. Hope for the best. Do you guys hear it out there, or is it only over here? It's only this thing? Okay. Now with 2 kids, all I hear is white noise nonstop. Stupid white noise machine, so I can't hear where it is. All right, I think that's better. So the quiz, I wanted to go over a few, or each month or Tuesday, I'll go over some of the key points of the quiz. So hopefully everyone was able to complete it in time and didn't completely forget about it. If you did, remember, like, these quizzes are benchmarks just to keep up to date with the class. Like, they're worth a very minimal amount of stuff. Solution there, unplug it. Still here. What? Here, let me try this. Okay, I don't know. Maybe that's it. All right. So, but at the beginning of each Tuesday, I still want to go over some of the key points of the quiz. Maybe you guys noticed this too. If you work together, you weren't supposed to, but if you did, it comes from a quiz bank. So your questions are all going to be kind of a similar format, but you're going to have different numbers. So these were the ones that were kind of the hardest hitting with like the lowest level of difficulty. I get all these fun statistics. If you're a statistics nerd, you get to see all this breakdown and stuff. But basically, I don't want to go over everything, but I still want to go over some of the key parts. Also, if you didn't notice this too, when you take the quiz, I don't know if it says this in Canvas. I don't know what it says on y'all's end, but they're due Friday at midnight. Saturday, first thing in the morning, it's open for you to review the solutions. And then it closes Sunday night. So you have the weekends. And if I didn't say that, I'm sorry, but just know moving forward, like you have the ability to review your solutions once the quiz is past due on Friday midnight. So yeah, Saturday morning, it'll open up and you can actually see that, but then it'll close again Sunday night or on Monday. I don't remember the exact time. But regardless of that, I'm going to try to go through if there's something on each quiz that it's like, oh, everybody like jumped up on, or there's just like a big like misunderstanding, that I want to make sure to go through it in class. So with these, I guess it's asking the same thing. These were the two. I just kind of took a screenshot from them really quickly, where maybe these are what your numbers look like. Maybe there's something different, but at the end of the day, this was the void ratio question, where we are given a total amount of soil and then a solid portion and then a portion of water, or of water, and then solid material and then the portion of water. Yeah, so with this one, void ratio, void ratio is the volume of voids divided by the volume of solid. And so we're given a total volume of these. And then we're given the volume of solid of 1.5 cubic centimeters. So I'm just going to use this one at the end, even though it's the same. So 2.25 cubic centimeters. And then we're given a total amount of volume of water. I feel like I snipped something off here, but there should have been a fully saturated. Did this question say fully saturated or assume fully saturated conditions? Was this one? I didn't even take a screen. I was literally just rushed because I was putting this in there. Was this a problem that had the like multiple choice numbers? You guys remember that? Okay, so there was no like one that said like none of the above. Okay, well, I'll double check in this one then, because this could be misleading and that could be my fault, and that could be why this is low, and I'm really realizing it's real time. So what like you would do in this case, obviously we know we have a volume of water of point whatever, 0.55 or 0.1. So for that, like we have this volume of solid. Oh no, okay, I see. Never mind. That's my bad. All right, so really this isn't as important information. What we know with a volume of total is it's going to be equal to a volume of solid plus a volume of void. I'm sorry, guys. And so with this, the volume of void is going to just be equal to the volume of total minus the volume of solid. So in either case, even though we're given this, we don't really need it for this specific one because all we need is the volume of void here. So once we calculate the volume of void from this, then we take that, we can plug it back into our void ratio equation. Sorry, it's been a day. I screenshotted this like literally a second before, so it took me a second to remember all of this. With anything too, I'm going to be going over these crash course. Like if you guys want to go over the quiz in more detail, please like don't hesitate to email me about it. And we can meet or set up a meeting, or I have a lot of these solutions kind of broken down because really, again, these quizzes are meant to keep your understanding like kind of up to date with everything. All right, is this clear, at least in this part? Cool, cool. All right, last week we ended on, let me just double check and see where we ended. So we got through one example and then for phase diagram. And just to kind of recap big picture with the phase diagram, soil is completely different than steel and concrete and other types of similar engineering material because it is completely variable. So it's all natural most of the time, and there is just more variables within it that we don't control. So in order for us to define and allow us to use some of these mechanics to establish these designs and do the engineering stuff in soil, what we need is the ability to define some of the physical characteristics with numbers. So the way we do that is through indexing. And a lot of these are these common ones here, like densities, void ratio, porosity. We went through those last week. They are all very basic calculations or very basic numbers that define the relationship of this phase diagram of soil. So what we do, we first assume that soil is made up of 3 parts. So even though it really looks like this, we summarize it and we categorize it into a solid portion, a water portion, and a portion of air. And remember too, we had some of those assumptions that this was based off of. So who remembers any of those assumptions we talked about last week, if you could say?
Air, water, and solid.
Yes, yeah, down here, air, water, solid. What were some of the assumptions that we made based off of that?
The raw materials in that like SSD state, or like where it's not absorbing any water.
Yeah. Not even that it's in an SSD state, it's non-absorbent. So it's small enough that we're just dealing with a single grain of material that like when water flows into the soil, it's only flowing into the air portion, the void. No water is absorbed in the solid portion. So it's just small, like too small of a material like that.
Also looking like the air, or like mass.
Yeah, we assume that the air has a mass of 0, so it's just normal air, which might not always be the case. It might have different densities. It might be like a gas. It might be whatever, a pollutant. Same with the water too. Most of the time we're assuming that the water is just going to be our normal high quality H2O, nothing like crazy, nothing mixed into it chemical wise or anything. The other portion too is that the solid is an average, or it's assumed to be a homogeneous material. When we know that's not the case, if you took a scoop of sand outside, you'd look, there's a bunch of different colored rocks, the different types of minerals. But what we do is when we do the different analysis on the mineralogy, we're looking at like the average or just the most prevalent material. So it's a homogeneous material. And that's really important when we talk about specific gravity of the solid. So we only do 1 GS, which is technically a GS average, where like for our concrete and for aggregate, we looked at GS, SSD, GS, all these different things, apparent, effective, all of those. So the whole benefit of finding these, again, think big picture, is to allow us to correlate to different types of physical behavior using a number. So dry density, just to recap this again, dry density is gamma, which is weight over volume. So this number correlates to how compact the material is. And why might we care for a soil standpoint how compact the soil is or how dense the soil? What did I say last week about the strength of it?
Denser it is.
Yeah, the more dense the soil is, the stronger it is against shearing. And it's because soil is frictional. So just like the more pressure you put on sandpaper, the harder it is to move away from it. We're increasing that normal force, we're increasing that density. These particles are going to want to interlock with each other and not roll and slip past each other and cause failure. Void ratio is, as we said in the quiz, that's the volume of voids divided by the volume of solid. And that is a way of numerically defining the compaction. So what we're looking specifically at in its natural state, how much volume of voids is there compared to the solid portion? So a higher void ratio means what in our soil? There's more voids than, yeah, so less compact or looser material. So a higher void ratio means the volume of void is big, the volume of solid is small, which means there's more voids, which might mean looser material, less dense material, generally less like strong material. Porosity is very similar. That's the volume of voids divided by the total volume. So volume of voids divided by the total volume. This is used a lot in permeability analysis and to understand the flow of soil or flow of water through soil. This is also shown as a percentage, just because. The degree of saturation is how much water is in the void space. So that's volume of water divided by the volume of voids. And then the saturated density is if we replace all the air and replace it with water, what is this new density? Obviously, water has more mass than air. So if we were to remove this air and just fill the whole thing up with water, then what would be this new density? What would be the new mass, even though the volume's not changing? Yeah, it would go up. Yeah, it'd be more dense in that case. Yeah. So if all of this is super foreign or you just had a crazy weekend and forgot all of it, please remind yourself or refresh. But as I said, we're going to be on this topic for a little while and then we'll see how these indices are used in design. But we ended with one example problem last class, and we will do the others here. So yeah, let's do this example problem here. Did we end on this one? I don't think so. We only did one example problem last class, right? Okay. So yeah, let's do this one here. So what we are given is the density. But it's in this weird looking row thing. So that means our units are in everybody except American units. So we are in grams per cubic meter. Our moisture content and our specific gravity are shown. We're asked to find dry density, void ratio, porosity, degree of saturation, and saturated density. So just first and foremost, what was I say that said what did I say last time is the first thing that we should do? I mean, convert or just like make sure you know what units you're working in. Why do we care? Like what's the variable that I said is mixed up a lot?
You're dividing by like 62.4 divided by.
Yeah, exactly. Yeah. So the unit weight of water or the density of water, like that's going to be the thing in any one of these problems, any geotech problem, you're eventually going to need to use the density of water or know the density of water. So make sure you use or you write down the correct one at the beginning. So in this case, the density of water is what? Yeah, 1,000 kilograms per cubic meter, or in this case, 1 megagram per cubic meter. That helps because we know specific gravity is density over density. So always try to match whatever units your density is given in automatically. So that means if we're working in this space, our dry density will be in what units? They'll be in something megagrams over cubic meter. Same with our saturated density too. Something megagrams per cubic meter. Remember too, mega is million, so times 10 to the 6. But if you're working just in the mega space, you're fine there. Okay, so we're given the moisture content, we are given the specific gravity, and we're given the density. So what I did for this one, since we're given the density and we're not given a total volume, and we're not given an initial mass, luckily the density has both of these things. So it is 1 megagram or 1.76 megagram per 1 cubic meter. That's what that is telling us. So our total volume is going to be 1 cubic meter. And then if we do that, our total mass is going to be 1.76. So that's that first step. At least we have the outside portion of this. Now we need to find a way to put things inside and complete it. So what we're given is the moisture content. And just like last time, we know this is 10%. Or if we're doing calculations, then that's 0.1. And this is equal to the mass of our water divided by the mass of our solid portion. And we need both of those, but we have one equation with 2 unknowns. So we don't know mass of water and we don't know mass of solid. But what we do know is the total mass over here. That's helpful. So our total mass is our mass of our water plus our mass of our solid. And we know that this number is 1.76 megagrams. Again, all those times we needed to use algebra, or we learned algebra and thought, oh, we're never going to use it. Well, at least you'll use it in this class. So we have 2 equations with 2 of the same unknowns. So we can rearrange one of them and then trick the other equation to help us solve for one of those. And then once we know one variable, then we can plug that back into our original one and boom, now we know both of them. So I'm just showing these 2 equations here. We'll put them together to look fancy like this. And I'm just going to include the units. So 1.76 megagrams per cubic meter is equal to the total which if we plug and rearrange our moisture content is equal to 0.1 ms plus 1 ms divided by 1 cubic meter. So this is obviously equal to 1.1 mass of solid. So boom, now we have this is equal to that. No, mass of solid. You could use either one though. If you wanted to rearrange this to solve for mass of water and plug that into there, or solve this for mass of solid and plug that in there so you only have mass of water, you know, either one, either direction. Okay, so when you plug that in, we find that the mass of the solid portion equals 1.6 megagrams. And then you can either use subtraction or you can do whatever you want, but let's just plug this in to our moisture content equation. Or no, well, let's just plug that into this. to solve for our mass of water. So we know that mass of water plus 1.6 I'm sorry, guys. I hate the Gators as much as anybody else, but this is it's the only colors I have. Okay, so we just used algebra to solve stuff. So that's good. That helps us solve everything on our mass side, because remember, this portion is equal to 0. So our air is equal to 0. So now, remember last time we talked about this, when we go from mass, how do we get our volume? Yeah, a little density triangle, D equals mv. So we use our density, or what is this? Specific gravity, which is, it's just density. Yeah, it's just a fancy like universal way of showing density, because we divide it by the unit weight of water. So it's the same like meaning, it's just a unitless way of showing it. So we have to transfer over from that side. So let's do the solid portion first. So with this, the specific gravity of solid is really just specific or the density of that solid divided by the density of water. So if we wanted the density of our solid, this is just equal to the specific gravity times the density of water. So we need volume. Which volume is equal to the mass divided by the density. So for the volume of solid, we know that we just found the mass, or that'll be the mass of solid. And then what I'm going to do is just plug this in to the denominator here. So the density of solid is just GS times the density of water. That's a W. So you'll see this equation here in this form a lot. But what I would recommend is not trying to memorize that equation, and more so just memorize how to get to it, if that makes sense. Like all it is the volume mass divided by density. And then the density of our solid is the GS times our unit weight of water. So in our units, it doesn't matter because it's 2.7, because we're using SI units. But if we were using US units, then that number is going to be different because we're multiplying the GS times 62.4. But for this case, this equation looks a lot prettier. And so volume of solid, VS, is equal to 0.593 meters cubed. And then we can do the same for the volume of water. Which is just the mass of our water, which we just found. So now we have solid and our air. We can find our our water and our solid. We can find our volume of air because we know the total volume, and then we know the volume of solid, and we know the volume of water. So if we plug this into our Excel spreadsheet to do this hard math, we get 2.47 cubic meters because this is 1 cubic meter. So I know for a lot of us, probably SI units are foreign just because we're not used to seeing M and G in cubic meters. But in this analysis and in soil analysis, it really is easier because density of water is most likely going to be 1. So that means our density of our solid is just this times 1. You know, the numbers are a little bit easier to comprehend. Sorry. Okay, so now you'll see up in the top right, we have all of our things completed. The only thing I didn't show was how to calculate this, but hopefully it's pretty clear from our little diagram there. The volume of void is just that air portion plus the water portion. You saying something to me? So the volume of void is just the volume of water plus the volume of air. So just from the little diagram here, you see the arrows are just those two on that part. So now all we need to do is just find the values, like the indices that we need, that we're asking. So once we have everything complete here, let's go ahead and solve for it. So our dry density, the first part, that is our mass of our solid portion divided by the total volume. So dry density is telling us, like, if we were to remove all the water, then what would be the density of this material? So the solid portion is the only thing that has mass because the air doesn't have mass. And the total volume in this case, again, it's nice units here. So this would be 1.6 megagram divided by, and I'm just going to show this just because in this case it's 1, but it might be something different, divided by 1 cubic meter. So our dry density is 1.6 megagram per cubic meter. Cool. Okay. So our void ratio, remember this is shown as E. This is our volume of voids divided by the volume of solid portion. So our volume of voids is 0.407 cubic meters. And our volume of solid down here is 0.593 cubic meters. We're both in cubic meters, so that's good. Those cancel out. And we get a nice 3-digit decimal place, 0.686. So what does it mean if we have a void ratio of 1?
It's all good.
If we have a void ratio of 1?
There is no void. Yeah.
No, it doesn't mean anything. It just means our volume of void is equal to our volume of solid. Remember, void ratio doesn't really have like a true physical meaning because it's just these two ratios here. It's not like moisture, or it's not like porosity that actually has a physical meaning of like 0 to 100%. So if we have a void ratio of 1, cool, that means our volume of void is equal to our volume of solid, but it doesn't necessarily have anything. So this number can technically be from 0 to infinity. 0 meaning there is 0 voids, because 0 divided by something is 0. And then the infinity side is there's no solid portion. So something divided by nothing is that error, whatever that pops up in Excel or in your calculation. So technically there's no like bound there. That would just be open space. But that's that tricky thing between these two. The physical meaning, porosity or void ratio doesn't really physically mean anything right now that we understand it. It'll hopefully make some more sense further on down the road. But porosity is the other one. This is that N that is very similar and has a little bit more of the physical meaning. So this is our volume of void divided by our total volume. So this is 0.047. This is 1. And we show it in percentage form because this one actually means something. So our N is equal to 40.7%. So if this was 1, then that means our volume of void would be equal to our total volume, which means it's nothing. It's all open space. There's no volume of solid in there because our little diagram over here on the right, this would be equal to that. So that would mean volume of solid is gone. Yeah, void ratio and porosity. So the other thing that they're asking is degree of saturation. This has to do with our water. So this is our volumetric index for the volume of water divided by the total volume. And so our volume of water is 0.16 cubic meter. And sorry, this is not correct. That should be volume of voids underneath it. I'm sorry, guys. Volume of void. So this would be 0.407 cubic meter. So this again has a physical meaning behind it. So we multiply it by 100, show it in percentage form. It's basically telling us how much of our void space is filled with water. So 0 saturation means completely dry. There's no water. 100% saturation means there's no air. It's only water. So in this case, obviously we're going to be somewhere in between. It's equal to 39.3. Sorry, that's a 3. %39.3%. So the only other thing that we have to find is this saturated density. Now this one's going to be requiring a little bit more just thought of what this value actually means to calculate. So I'm just going to go to the next slide. You can complete it there if you want, but just so I have enough room to write, this is the 4/4 in the top right that you should have. So what our saturated density means, you'll never guess this, but it's the density when the degree of saturation is 100%, which is crazy, right? Blows your mind. Saturated density means density when the degree of saturation is 100%. So this means if the degree of saturation is 100%, this means our volume of water is equal to our volume of voids, which again means that the volume of air is equal to 0. So there's no air here. So I showed this equation earlier, but what this means here is our degree of saturation is the mass of water, but I'm going to put a little asterisk here because it's the mass of water when all of our void space is filled with water. So mass of water plus obviously the mass of our solid divided by the total volume portion. So this mass of water is if, or maybe when, the volume of void is completely filled with water. So that means if we're over here on our mass side, over here, looking at this again, technically what we're talking about is this is our mass of water asterisk there. Mass of water asterisk. So the current mass of water we have is only a portion of the void space filled. So what we need to do is using density going back over to the mass side, but assuming the volume of void 0.407 is filled with water. So we have to go the other direction now. So luckily, we're in the right units here. The mass of water is, or sorry, the density of water is 1 megagram per cubic meter. So the mass of water here is going to be equal to the volume of void times the density of our water. Is everyone seeing where that's coming from? We're using the subscript volume of void because, again, we're saturated state is assuming the volume of voids is filled with water. So the volume of void is equal to the mass of water. So let me just make that note here. Because of this equation here for saturated. Okay, so this equation is easy to fill out though. So our mass of water when we're 100% saturated, and it's nice because our density of water is 1 cubic or whatever is this right here. So it's just equal to our volume of void of 0.407 megagrams. So what we can do now is actually plug this in. Plus our mass of our solid, 1.6 megagrams divided by 1 cubic meter. So that'll be our saturated density. And as I forgot who said it, but remember saturated density, we're adding more thing that has mass. So it should always be a larger number than our dry density. So it should always kind of go like this. Dry density should be smaller than our normal density, should be smaller than our saturated density. Same thing if it's a gamma. Same thing if it's unit weight, not density. So think about this. If you do have questions, let me know right now, but think about this whole thing right here, because this is an important concept where this saturated density is assumed because we have saturated conditions. So like, don't try to memorize that equation. Think more so about why it's like that.
Why don't we care about this saturated density?
So a lot of times we would still calculate the saturated density based off of the groundwater table rising. So like, let's say right now you collect a soil sample 5 feet down, but it's not in saturated condition. So like, what would happen to that density? What would happen to the weight that it places if it's saturated? Another case would be like, not only for current in situ stress, but also like loading. So let's say we're building a structure that has to put like 6 feet of fill on top of it. And let's say like there's some structure underneath it that like that 6 feet of fill could potentially break that structure, like a utility line, an old tunnel or something. So the soil coming in might have a set like normal dry density, but in Florida, what happens if it rains? That could become saturated density, and then that could be too much of a density or too much mass that then breaks our tunnel underneath it or something. So you'd usually account for it, especially in Florida, just in case like the groundwater changes or rain. Okay. So we're going to continue on in this kind of thing for this lecture. Again, that was the lecture notes from last time. So same thing, and I kind of already covered this stuff, so I'm just going to go really quickly. But if you want these, again, these were those assumptions that we talked about at the beginning. So I'm just going to write these down again, just in case. Homogeneous, which means the P is the same throughout, or sorry, the solid portion is same throughout. And also the solid is non-absorbent. So those are those assumptions that we do for our phase diagram. And density is a huge thing. Density is a huge thing that allows us to did anyone actually see this in grade school, that density triangle, or did this just shape my childhood? You did? Okay. Maybe it was like a Magic School Bus thing or something. I don't know if you guys were too young to watch Magic School Bus, but could be a Miss Frizz patent tape, you know. That's like one of the things I cannot wait, like for our toddlers, our kids to be old enough to actually watch and appreciate this stuff, or they're just going to make fun of it completely. But that show, solid. Bill Nye, oh, I still tear up when I hear that. One thing though, reading Rainbow, anybody? No way, dude. That it was a little too creepy there for me, but that's why I'm an engineer, because did not like the reading side. LeVar Burton. Anyways, okay, I don't want to do. Tomorrow's a snow day, so I don't want to do it tomorrow. Okay, so this is all back like makeup stuff from last time too. Talked about these and which ones make sense, which ones do not. And then I shared this here too at the end. This is if you were to like print one slide out and put this on the front of your notes or hang it on your wall or put it on your mirror so you see every morning. This is one that would be very helpful to do. Because remember, like all of these numbers make sense, but you're going to be calculating these numbers and these equations quickly, I should say, like either in practice or during the FE. So understanding the typical ranges is important, and as well as the units is important too, because that's going to help you notice you made a mistake or notice you potentially make a mistake before you get knee deep into the calculations and doing all the analysis and design work, and then realize your one input parameter is wrong. So like understanding the typical range and the physical values of degree of saturation, porosity, void ratio, like the different ranges there, especially this little section here, that will help you tremendously on the FE. Yeah.
I think that will go over like the void ratio more depth later on, but it's the point of it, like since it's dimensionless, you can like use it in different equations. So like what is the
Yeah, that yes, it is. It's it helps, like I mentioned, like kind of correlating it to a scale. like it allows us to kind of compartmentalize different ranges of behavior. Like, so like 0.1 to 0.5 experiences this behavior, kind of how like a hurricane scale allows us. So it helps in communication, it helps in equations, but it also helps us scale from a field setting, or sorry, a laboratory setting where we're doing a little sample or testing a little piece of sample, helps us scale from this small little sample to an actual like large field or the whole site conditions. So that's why all of these values are super helpful, is we can find them in the lab and we can do our test here in like a nice air conditioned lab, and then use those same values to describe the physical behavior at the project site. Okay, let's see. Did I go over this one already? 1.76. I may have just copied the slides over the wrong spot. I think that was the first one we went over. It just looks a little bit fancier. Yeah, that's the one I just went over. So that's the same thing that you just wrote. Sorry to include you. If you saw that ahead of time, then good for you. But if you didn't, then you got writing behavior there. So yeah, these are all the things we just went over. So if you missed my writing at all, then you can put that in there. Let's look at an alternative solution to solve this one though. So one that might be potentially easier. So in this case, what we first did, remember in the last one we just did, we were given the density and we assumed a total volume of 1 and then a mass of 1.76. The page here. So let's look up an alternative solution. I used to have a picture pop up of Blink 182 right there, but now they're not alternative anymore. It's like coming back. So what we can also do through this, and again, this is where I was saying like the phase diagram, the whole point of it is to eventually fill everything out so you can calculate these. But there's different ways to get there depending on like what's given, but then also depending on how your brain thinks. So what we can also do is assume a volume of solid of 1 cubic meter. So, or just one anything. If we were working in cubic feet, you could do this at the very beginning. So let's go through this right here now. So if we assume a volume of solid of 1 cubic meter, then what would be the next step, or what equation here could we take to help us solve for the next thing? Yeah, I'm pointing to it to help in this. So we could do a few things. Yeah, so first what we could do is find the mass of our solid if we assumed a volume of solid of 1, right? Because we're given the density of solid, because we're given the specific gravity of 2.7. So boom, right off the bat, we have volume of assumed, and then we're going to go over and find our mass of solid there. So then also what we can do is, using our moisture content, we can find our mass of water. So if we have a volume of solid of 1, we can find our mass of water easily because it's just 0.1, which is 10% our moisture content, times mass of solid. So mass of water is 0.27. So boom, we just found it that way. And kind of see where the next step would be going. What would we next do here? Yeah, we would go from mass, and we can find our volume of water now because we know the density of water, and we've all memorized that by now because it's the 3rd week and we're engineers. So yeah, this 1 megagram per cubic meter. So we can find our volume of water that way. Now we can also find our total mass, because remember this is 0. The air portion is 0. So we can find our total mass of 2.97. So 2.7 plus 0.27, everything else is 0 there. And so we're almost going backwards, where now the only thing we need to find is, yes, our volume of air, but we also need to find our total volume. And remember, last time, the first thing we did was use our density up here. But now we're going to use our density based off of the calculated total mass to find our total volume. So our density that was given to us is our mass divided by our total volume. So our total volume, which is now calculated, in this case is 1.688. So at the end of the day, all of these should be the same because they're all scaled differently. It's just depending on where you start. Now, what's the apparent like benefit of going this way? Yeah, we get the total right off the bat, but also we never had to set up those two systems, those two equations, two unknowns, remember? Which is perfectly fine. Like we get the solution that way, but this allows us to set up and just kind of go one by one. Now, this only works though if we're given a density and we're not given a set total volume or a set mass. So in this case, if we were to get like one more piece of information, let's say we're given a density and then we're also given a total mass. But we can't do this. We can't assume a volume of solid because we're given a value already to plug into there. So we can find our total volume, or we just found our total volume. We can find that last one, or volume of air. It's usually always the last thing you find. And so that will be the total volume minus the volume of water minus the volume of solid. And we get our volume of air this way. So boom. So although the numbers look different and our phase diagram looks different here, like these indices will all be the same still. So this actually has another benefit by looking at it this way. Oh, never mind. Okay, yeah. So this is the alternative solution there. So let's look at this other example here of another way basically of just solving this stuff. So in this case, we're given a void ratio, we're giving moisture content, and then we're given the specific gravity of solid. The next thing we would do is boom, write down our water just to make sure we're in the right units. And then just not to complicate anything, since we're given the density of our solid portion, just remember our specific gravity is that divided by water, so it's 2.65. So I'm just going to write that there. Sometimes it might just be given to you that way. Okay, so since no volume is specified here, let's assume a volume of solid of 1. So we're not really given anything in the mass or the volume. We're only given densities. So let's just assume the density, or sorry, the volume of solid in this case is 1. Let me just make sure I'm not like double writing on anything. Okay, so since no volume is specified, assume this, which also has a benefit because remember, we're given our void ratio of 0.62. This is equal to our volume of void divided by our volume of solid. So right off the bat, if we're assuming this, this means our volume of void is just equal to our void ratio, which is equal to 0.62. Remember, this is our volume of void right here. And so this is equal to 0.62. So this is kind of cool because then in this case, sorry. So this means our total volume, which is equal to the volume of solid plus our volume of void. Our total volume would be equal to 1 plus our void ratio. Which is equal to 1.62. And I'm writing it this way out because you'll see by making this initial assumption here, volume of solid equal to 1, this allows us to express our total volume through a 1 plus our void ratio, which will play a role in the equation development here in the future. But just for now, right now, like we'll just say that, all right, so this helps us calculate it's 1.62. So that means over here, yeah, volume of total is 1.62 over here. So we're gonna now go, so we've just found our volume of void, our total volume, and we can also then find our volume of air from that. And now we can go from our mass, or we can calculate our mass over from our density. So the mass of the solid portion is equal to the volume, which is 1 cubic meter, times our density of solid, which is 2.65 megagram per cubic meter. It's 2.65 megagram. Sorry, that should be a capital M. Our total mass is equal to 1.62 megagrams times wait, did I do that wrong? Oh, I'm sorry. We need the or from our total, or we can find this from our moisture content here. So sorry, I skipped this part down here. So using the moisture content, we can find everything else. So our moisture content is 0.15. So the mass of our water is point. Okay, so I'm not writing them in here, but we found our mass of solid, we found our mass of water. We can then find our total mass because we can add those two together. Sorry guys, running out of room, but that should be 3.048 megagrams. So now we found our total mass. So we know our volumes as well. And we can find, since we know this, we can find our volume of water due to the density that way. So on the next page, we'll start calculating this dry density. So for our dry density, we know that's going to be our mass of our solid divided by our total volume. Now, since we assumed this Vs equals 1, our mass of our solid is just equal to the density of solid, and our total volume is equal to 1 plus our void ratio. Oops. So again, total is 1 plus here. So let me add this here. So since we're in SI units, or no, not even that, I'm sorry. Since our volume of solid is 1, technically this is times 1. That should be plus or times 1.0. So this allows us to make this helpful equation. So our density is equal to our density of solid over 1 plus our void ratio. So likewise, though, so this is also, just because of this assumption, we can set up an equation that is easier to calculate these dry values based off of our void ratio. So this is already one of those indices that allows us to use void ratio. So if we're plugging this in here, I'll just do this real quick, 2.65. 1 plus 0.62. So this is equal to 1.636 megagrams per cubic meter. Okay, sorry, I don't want to I'm already losing a lot here, so I don't too into it to finish off this example problem. So we've already found our dry density. So we'll do this Thursday, the rest of it Thursday. But keep in mind here, so the reason why we're doing it separately here, if we assume VS is equal to 1, then what we can do is set up equations to act as what I'm just going to call a shortcut. And this is all because of the void ratio. So this is, again, explaining why we care about void ratio sometimes over the porosity as engineers. Is this void ratio will allow us to then correlate to some of the densities. So just like how this equation here, if we knew our specific gravity of solid or our density of solid and we found void ratio, then boom, we could find the dry density right here. Or vice versa. If we knew our dry density, our solid, then we could find our void ratio. So we're going to be setting up equations that look very similar to this that then will allow us to either check our work or will allow us to calculate it, if we're not given all of this information up here. So that's big picture. Sorry again to end in the middle of a freaking example problem. Enjoy the snow day tomorrow, and I will send an announcement on Thursday. If you're on the Thursday group for the labs, please still go to those because we're still having them on Thursday. And you can view all this stuff on Canvas. You can download it ahead of time and review it as well, like the stuff for moisture content.
What time is it Thursday?
I think the first one.